Good afternoon, everyone. This is the first press conference this afternoon, the fourth today, and it's on mitigating tsunami risk with early warning systems. And we have three speakers on the panel. One is Anthony Lomax. He's an independent seismologist, seismological and software consultant in France. Andrei Babejko is a researcher at the Helmholtz Center in Potsdam in Germany. And Jürgen Mosgraber is a researcher at the Fraunhofer Institute of Optronics, System Technologies and Image Exploitation, also in Germany. And each of you should give a short presentation, then we'll open the floor to questions. So, Anthony, you can start. Thank you.
Thanks. Start by... Is it that one?
No, I think the PDF one. The one on the right. I think it's
it's a PDF, so it's that one. Oh.
Yeah.
Okay, and then where's slideshow?
One above. That one, yeah.
There. Okay, good afternoon. Anthony Lomax, software consultant, seismologist who's become a scientific software consultant and earthquake and seismology consultant. And also my co-author is here. It's Alberto Michelini, who's a seismologist at INGV, the Italian National Geophysics and Volcanology Institution. So I'll present our work, the work we're presenting tomorrow at this meeting. The main title is Tsunami Early Warning Within 5 Minutes. That is the idea that we are seismologists. We're working, in our case, entirely with earthquake seismology measurements that can today be obtained very rapidly in real time after a large earthquake, almost any place in the world. And so the idea is, what can we do with our seismological measures in order to give information to whoever's responsible that can aid in giving a very early tsunami warning. A secondary part of our presentation tomorrow, and I'll mention today, is that as part of this work, we also, a little bit later, within 10 minutes, we can estimate the size of, we can get a very good estimation of the size of very large earthquakes, these megaquakes like the earthquakes 2 weeks ago and the Tohoku, Japan earthquake, and the 2004 Sumatra earthquake, earthquakes that reach the size of very large magnitude 8, magnitude 9. And I'll discuss that a little bit more. In summary, these procedures, which use earthquake data currently available for most parts of the world, earthquake data that comes in real time within seconds after when it was recorded on the ground. The first part is that we estimate within 5 minutes after an earthquake occurs the potential of the earthquake to generate a significant tsunami. And we do two main measures for that, which I'll show in a moment. And then the second part is this magnitude estimation. Within 10 minutes after the earthquake, we estimate the magnitude I mentioned, which is called MWPD, and this gives the true size of these very large earthquakes. So the information within 5 minutes would be part of a decision perhaps to issue a very early tsunami warning. The determination within 5 minutes after an earthquake occurs of the true final magnitude aids in many decisions and modeling that happens early on after a large earthquake to aid in tsunami, but also earthquake activities that happen soon after a large earthquake. And also, these measures we make, I note on bottom there, it also provides basic earthquake parameters for people who are doing some more sophisticated modeling, quite sophisticated computer modeling. This gives basic earthquake parameters so they can start very early in doing a first pass of their modeling, because some of the other information they need doesn't come until about 20 to 30 minutes after the earthquake. And in particular, there's early tsunami forecast modeling that is of interest. That is the computer modeling that will predict as quickly as possible what are the likely wave heights along coastlines that may be affected by a tsunami caused by this earthquake. One major point I want to make, we are seismologists. We're measuring seismological information. Seismological information from an earthquake is about the first information you get for earthquakes anywhere in the world, because earthquake waves travel very fast. But what we don't really want to understand the earthquake rupture, the earthquake itself. What we want to understand very quickly is what is the seafloor uplift caused by the earthquake, because it's a seafloor uplift that causes an ocean displacement, which becomes the tsunami. However, the standard earthquake magnitude that we're all familiar with is not directly related to the seafloor uplift produced by a large underwater earthquake. So here I have somewhat of a cartoon figure of a dipping fault, which is the kind of fault that slipped in Japan in 2011, Tohoku earthquake. And I put in green here two sort of cartoon earthquakes, a deeper earthquake, and here a long, shallow earthquake right near the surface where the fault reaches the seafloor. And the basic point is here that these two earthquakes have the same magnitude. Seismologists, we talk about seismic moment, but the magnitude that is finally reported as the magnitude of these big earthquakes is called moment magnitude. So it's number related to something called seismic moment. What's important is the magnitude of these two earthquakes can be the same, but the seafloor uplift from this earthquake, it's over a broad area, it's of small amplitude, and it will lead to a small tsunami. And in many cases like this, a tsunami that does no destruction, no significant effect on coastlines. The other extreme, a shallow, long earthquake, a lot of seafloor uplift, and these kind of earthquakes produce a large tsunami wave, comes into nearby coasts, and these are some of the more destructive earthquakes and causing seafloor uplift, causing tsunami. So this is the case that's the most dangerous and the most effective at producing large tsunamis. So the goal of our early measures is to distinguish between these two types of earthquakes in the way that the standard magnitude does not. Another point I want to make that I refer to a bit later is that this moment magnitude, as it is now determined in a standard way, is available 20 minutes or more after the earthquake. So now I'll show a little bit technical seismograms, but you don't have to understand much. But I'll show seismograms from real earthquake data, real seismogram data that can be collected in real time from earthquakes at the present time. I'll show a seismogram from an earthquake like this, the shallow earthquake that could cause a large tsunami, and I'll show a seismogram from an earthquake like this that would cause a small and non-destructive tsunami. So the upper part of this figure is our seismograms from an earthquake that causes a large tsunami, and the lower part is from an earthquake of the same magnitude that did not cause a significant tsunami. The main point is that we make two basic measures. These measures are made within the first minute after the first earthquake signal is recorded on these seismograms. So these seismograms are data that are recorded at stations at 10, 28,000 kilometers from the, 1 or 2,000, 3,000 kilometers from the earthquake. These signals come into the stations within a few minutes. We make measures on the next minute or two of these seismograms. So we're basically working within 5 minutes after the earthquake has occurred. The first measure we make is just the period of the beginning of the seismograms. The period is the distance between the peaks and troughs, the main peaks and troughs on the earthquake recording. So we measure that. Here's a cartoon measure on the tsunamigenic, the earthquake that caused a large tsunami. The same measure on the earthquake that did not cause a tsunami. You can see that the peaks and troughs are much closer together. And that's typically what we see. The earthquakes that cause large tsunamis have a large distance between peaks and troughs, and the earthquakes that do not cause significant tsunamis have a small distance between peaks and troughs. The second seismogram I show for each earthquake is really the same seismogram, but we're only looking at the high frequency, the rapid motions. And basically from this we can see directly the duration of the earthquake. So in this case, this strongly tsunami generating earthquake lasted about 3 minutes, which shows up in the strong signal here for about 3 minutes. There's a 1 minute scale. The earthquake that caused almost no tsunami, it only lasts about 30, 40 seconds is this duration. But we go beyond that because we don't want to wait 3 minutes to say this is a very long earthquake. What we do for a quick measure is we just wait 50 seconds into the recorded signal and we say, yes or no, does it look like this earthquake is lasting more than 50 seconds? Simple, sounds simple, but it's a quick, direct, simple measure, and it's effective. Both of these measures, the period here and there. So going back to our cartoon of the mildly tsunamigenic earthquake and very strongly tsunamigenic earthquake, the combination of these two quick measures we make within the first minutes will, in general, give a much, much stronger signal, a much, much stronger value for this earthquake than for this earthquake. We've looked at hundreds of earthquakes in the past, and we differentiate between these two types of earthquake very well with our measures. And again, that's all available roughly within 5 minutes. The final result is available within about 5 minutes after the earthquake. The next thing is we have this measure of very large earthquakes, the true magnitude of very large earthquakes within about 10 minutes. Very quickly, I've already talked about, we were looking at the duration of the actual earthquake rupture on these high-frequency, rapidly varying seismograms. So we have this time of the earthquake rupture. Now, a standard magnitude, and one that is available very quickly and is used for tsunami warning, is called MWP. A standard magnitude is based on the size of one pulse on the early part of the seismogram. And all we do is we take this concept of measuring the magnitude by the size of one pulse on the seismogram, and we apply that, adding up this size from all the pulses up until this duration of rupture that we've been able to measure. So we get effectively, for very large earthquakes, which have long duration and they send out lots of pulses of energy, we try to collect all those pulses of energy, and that works quite well, and that's why we get the full size of these very large earthquakes. This measure is typically available within 10 minutes after even the largest earthquakes. And as I mentioned earlier, the more definitive earthquake magnitude that is used regularly, called MWCMT, is available 20 or more minutes after the earthquake. So we're giving a preliminary information on something that otherwise we'd have to wait 20 minutes or more for. And this information is very important for people who want to especially work on predicting how big a tsunami might be. So the last picture is it's a simulation of what we could have in real time after the Japanese Tohoku earthquake from using our procedures. This is a snapshot of a simulation at 6 minutes after origin time. The Tohoku, Japan earthquake, as everybody knows, is a devastating megaquake and tsunami. And the arrival time of the tsunami at the Japanese coastline is about 35 minutes after the earthquake origin. So here we're 6 minutes after the origin. 35 minutes is the arrival time of the wave. What do we have from these measures I've described? Our two quick measures on the early part of the seismograms show a very high tsunami potential. Our measure of magnitude, which I said is usually available about 10 minutes later, well, at 6 minutes we already have 9.2, which is effectively the final size of this earthquake. The definitive seismological magnitude is 9.1, but the difference between 9.2 and 9.1 is not significant seismologically. We additionally have something I haven't talked about, but it's called an earthquake mechanism. Here we use actually kind of an old-fashioned technique mixed in with our other calculations, and we get an earthquake mechanism which basically tells the seismologist the orientation of the fault that ruptured. And in the case of the great Tohoku earthquake, it's faulting like that. Japan is here, and there's a fault. And this funny ball-like symbol here would tell the seismologist immediately this earthquake is that kind of rupture, which is the most dangerous for tsunamis. And in particular, the earthquake 2 weeks ago in Sumatra was not this kind of rupture. So having this information also very early on could aid in people who are responsible for issuing tsunami warnings. Thank you.
Thank you, Anthony. We need to move on to the other speakers very quickly because we need to leave time for questions in the end. Andre?
So let's start now. I have to show the presentation. It's here. So good afternoon. My name is Andrei Babeyko, and I'm a scientific researcher in the Geoforschungszentrum in Potsdam. Since 2006, I was working on the development of the German-Indonesian tsunami early warning system, and just after the Sumatra event, it became clear for us that real-time GPS has enormous potential for the tsunami early warning. And that's actually what I want to show you also today, that how it could work, how it might have worked for the case of Tohoku earthquake. So my main point is that using coastal GPS arrays, a qualified tsunami warning may be provided within 3 to 5 minutes after the event. So actually, why we are not happy with traditional seismic-based tsunami early warning? So I would say two points. Point number one, seismic methods tend to underestimate the magnitudes in first minutes after an earthquake. So this is especially true for tsunamigenic earthquakes, either very large like Tohoku or Sumatra, or so-called slow tsunami earthquakes, which have enormous tsunami potential related to their radiated seismic energy. If, for example, you would look on the table at the bottom of this slide, then you see the timing of the Tohoku event. So the first 3 minutes after the event, GMA, Japanese Meteorological Agency, already provided a warning, major warning. It was very, very fast, only 3 minutes, but the warning was based on the magnitude 7.9. So there is a huge distance between 7.9 and 9. It's approximately 40 times smaller. But still, the earthquake was so large that even 7.5 provided a major warning, but only for 3 prefectures, and wave height was estimated like to be 3 meters. Then 9 meters, PTW, see this is Pacific Tsunami Warning Center, also provided warning with the same magnitude. 22 minutes, the new technique called W-phase centroid is 8.8, so it's much closer to the real event. And but for example, GMA upgraded the magnitude to 8.4, still much not enough, only after 1 hour and 20 minutes. So the point is that this is just physics, because to work with, to determine the true magnitudes, seismologists have to wait until the seismic waves would travel far away from the source. And with the GPS, we have a chance to sit directly into the inside the source and see the signals immediately. So this the first argument. The second is that from seismology we get so-called point source information, so magnitude and location. And if you look, for example, here, this is the rupture model. I don't see the mouse pointer, but actually here you see the rupture model of the Tohoku. Thank you. So this is Sumatra. Epicenter was somewhere here, but look that the rupture went north, 1,200 kilometers north, and the most destructive wave came to Phuket not from the epicenter, but from Andaman, Nicobar, and Andaman patches of larger slip. So for near-field tsunami warning, we need much more information than just magnitude and location. We need a so-called finite fault model, so how the rupture looks like. And that is exactly what we can get from the GPS. So what we have done, we have made a replay of the Tohoku event. So replaying means simulate the situation as it might have taken place in a warning center connected to the GPS array. So in this case, GeoNet GPS array, operated by Geospatial Information Authority of Japan, has a lot of stations. All of them are online, 1,200 stations. We used only part of them. So we took on input the raw observations from the GPS stations as it would be in the real time. Then the procedure, there are 3 steps. First step is GPS processing, convert GPS observations into co-seismic displacements. So this is original software developed at our institution. Is being used, and we have like delay time like 15 seconds. After 15 seconds, we have displacements. Then we can invert this displacement into the slip, into the rupture parameters. So this is inversion mathematical operation takes from 1 second to 1 minute, depending on what we want. And the last third step, if we have a source model, we can compute the tsunami propagation and impact. It could be also done very fast for early warning, like in 15 seconds. And then we repeat it. So now look at on the timeline, 60 seconds. So the earthquake was approximately for 3 minutes. So this was the duration of the earthquake of the Tohoku. After 60 seconds, plus processing time, as I said, we already see something. We already see some patch of high sleep, like a magnitude would be estimated as 8.5, and we also we already can give some forecasting. So these are warning levels which are being used for tsunami forecasting. 30 seconds later, magnitude 8.7. We see there much better. We see the GPS vectors are much larger, and we see the sleep much more larger sleep. Actually, warning perspective changed, and then 3 minutes after the event, actually, you see that this warning perspective, what is important for us for early warning, is now, I would say, saturated. It's more or less stable. And this is the final, what you see here on the right, it's measured data. So it's warning levels converted from the field observations. So we see that there is some difference in the details, but in general, I think that for early warning, it's absolutely enough. So, I mean, this is a GPS shield. This idea is not very new. It came from the beginning of this GeoTuse project. And actually what we show here, that it could be applied everywhere where the trench is located very close to the coast, like Indonesia, Japan, Cascadia. This is west coast of USA and Canada, Central America, Chile. So, thank you.
Thank you. Jürgen.
Okay, so my name is Jürgen Moosgraber. I'm working at the Fraunhofer IOSB, located in Karlsruhe in Germany, and I'm leading a research group called Architecture Information Systems, and that's what I also wanted to talk about a little bit today, which is architecture, system and software architecture in early warning systems. I'm working in a project called TRIDEC, which is a European Framework 7 program project, which got already presented last year at the EGU, and now we're in the second year and got some first results of a system. And so the question for system software architecture is we have a lot of sensors at the bottom, a lot of sensor data, for example, in a wide area, in a geographic area, and we need to have some magic to base on that a decision, is there an early warning necessary. So the question is, how do we design this magic? And there are some requirements for that. For example, we do not start on the green field. There are already systems available, systems we already saw before with some algorithms, simulations, and we want to connect these systems. We don't want to write them new, but we want to connect them. So one of the main thing is communication is the key. We need a resilient infrastructure to connect these systems. For example, if a system breaks down, we want still work and still want to predict, is there a warning necessary? And we need to handle big data, which means we have a lot of sensors. There's a lot of data arriving from these sensors, and we also, for example, want to store those data for later on research. And we also want to plan for extendability. For example, we want to connect new sensors, or if new algorithms arrive, as we saw before already, which is a better prediction capability, and things like that. Another thing is we want to be faster, as we also saw before in the talks, and want to automate our decisions. So a lot of stuff is currently done manually started simulations to check out if there is a possibility for a tsunami warning, and we want to look into is that a way to make it faster and automate this with computer systems. I will show that in more detail in my talk tomorrow, but I just wanted to show you two other things which might be quite interesting. So a new idea for a sensor is not a normal hardware sensor, but use a human. For example, there are already research done that if you're using Twitter, that if an earthquake is happening at a specific distance, the Twitter messages got faster than actual earthquake. So the idea is to feed that information also in the system and use that as a human sensor, and maybe better get some more interesting results. And another thing is how our idea looks, how we can improve the system speed up with the workflow. So we get those potential warning message into the system on the lower right, and then we want to facilitate something called a decision table. So we have a lot of numbers we want to check, and if they're in a specific range, we can say, okay, this might be a potential tsunami, and then we can automatically start several simulations at once and see if the fed-in data might cause a tsunami. And another thing we could do already is then generate automatic warning to users, so we can speed up the process, which needs currently a lot of officer interaction for the officer in duty. So thank you.
We have a question already from Christina.
Christina Reed, Discovery News. How many decision makers are currently involved in between the sensor and decision steps that are human? For Japan, around the world, all the different tsunami alert warning systems that we have, how many of them are actually determined by a human being, or are they all automatic?
I think I'll give you the best overview about that, or Joachim?
I can say, for example, for Indonesia, yeah, actually, so that usually this decision is being taken by the operators, which are working together with the decision support system. So decision support system takes all the information from all the sensors, evaluates this data for the quality, then usually asks for simulation. Please provide me a scenario of what is currently the most realistic, and then suggests a decision by the officer on duty, could change it somehow, so it's his, usually if you ask how many, that I would say it's like in the responsibility of a person who is currently sitting at the desk, and his responsibility is to provide a warning or not to provide a warning. So it's like a decision is being made by a person, but it's being also supported by the decision support system. So it's okay. But this decision would go, say, to. It depends on the land. For example, for Indonesia, this decision would be issued by the ministry, and then would go to the local authorities, and then also local authority would decide if we get the decision
Right.
further or not.
So we're seeing all this potential for making the sensors very quick, very rapid, GPS, and then it all still boils down to people and how fast the people can make those communications based on what the data they're receiving?
Sure, that's two routes. So first we need to make the way up till a decision can be taken. There are already a lot of people involved. For example, you have local warning centers, then regional warning centers, then warning centers in each country, and then the information needs to circle down to the people. So the second way we are not currently looking at, we're looking at a way to get the decision faster.
Any other questions?
Good afternoon. My name is Antonio Sanchez with EFE, the Spanish news agency. Are those new ways, these new methods to measure, being already implemented, being already used, to reduce the warning, the time to generate a warning? Or at least there is interest from the side of governments, public institutions to start using these new methods.
The methods I've presented are, they're running in real time on a research system in Rome, on INGV, so we're learning about it. They are, particularly the two early measures, which I think are in some ways the most important, they are very new, so it's very important that they are observed, studied, people consider them, so there will be, I can't say how much time or even how or they will be implemented in the future, but it's not, it's correct that for the moment they're in research system, we're publicizing them with meetings, and they are not yet part of any warning system with a responsibility to give notifications. But I think that's just correct. The other, you mentioned W phase magnitude, which is something that has come quite quickly over a few years. It's used by agencies that are responsible for reporting. It's a very elegant algorithm. It's the algorithm that now gives the magnitude of very large earthquakes in about 20 minutes. So that's the measure. In that case, it's not really so new because they're also finally getting a magnitude which everybody's comfortable with. So I think the time there is shorter. It's a very important measure. It is being used. Our measures, it'll be some time.
Any other questions? Any questions from the web stream? Or the room?
Well, the same question was for GPS also. The GPS measures, which I'm interested in the answers.
Actually, what I told about is implemented now in GeoTools, so this is in Indonesia. So we use there a little bit another way of GPS processing. It's not so fast as what I showed you today, but it's operational. And as far as I know, it's probably the only warning system which is operating also GPS. But I'm sure that there would be implementations very soon also in Japan. There is also a new paper came recently about also this story with GeoNet array in Japan. And also you told me that there is also ideas in Mexico, to do it in Mexico. So I'm sure it would be in next years, yes, because the accuracy of GPS now is fantastic. It's 1 centimeter could be measured almost in real time. It was not so 10 years before just because of this very, very rapid progress in real-time GPS accuracy. So now it makes possible to measure very small displacements. And that's what we need to invert for source parameters.
Are there any more questions? No? Okay. If not, thank you very much for coming. Thank you to our excellent panel of speakers. The next press conference is at 4, and it's on the Dawn mission and its latest results on the asteroid Vesta. Thank you.